first agenda item is Quark, one of our future wave architect. He's going to present a new container runtime. And then the second item is Fornex edge development contribution, which Click to Cloud team did, and they're going to present that. So I think let's do that. So Yulin, would you be able to cover this thing in half an hour, or is that something? How much time? Okay.
Yeah,
good.
Half an hour is okay. Yeah.
Perfect. Good. So I'm gonna give you. Hi, Professor Dusar.
Hi. How are you?
Good, thanks for joining. Yeah, good.
Thank
so
you,
I think we just started. So yeah, Yulin, go ahead, take over the screen. You can share the screen.
Yeah, let me share my screen. Oh, can you see my screen?
Yes, we can. Yes.
Okay. Yeah, let me start. Quark container is a high-performance secure container runtime. The goal of this Quark container is to run the containerized application in the container directly on the bimetal machine directly instead of go through the have another layer that's a virtual machine. The current that's environment, that's cloud execution environment. Normally we will have the container run inside the virtual machine, and the container provide the resource isolation, but we still need the VM to provide the secure isolation. But this VM introduce some overhead, for example, some memory, file I/O, and network I/O. And we hope we can run the containerized workload in the bimetal machine directly, so that we can save this virtual machine overhead. Yeah. For secure container, they have three dimensions. First is the security. That is for the Quark, it's just like a virtual machine. It is based on the KVM virtual machine based isolation, and it's developed with the Rust language. And another important thing is the performance. The Quark container is designed for the cloud native workload execution. It just any question? Yeah. Oh yeah.
Keep going. Yeah.
Yeah, it's designed dedicated for the cloud native workload. Yeah. So actually, for a container, it supports multiple. It is run inside the Linux machine. It supports many features. For example, the multicast network, and support different device. But for secure container, just for security scope, it's just dedicated for the cloud native workload. So we can do some optimization for that. Another thing is that it's optimized for data center environment. It's use the data center. It has development have assumption that it will running inside data center with data center network, and it will running with the multiple core that server. So we can do more optimization for that. Another important thing that we need to provide Linux capability. Yeah. So far the Quark container have support maybe 130 system core, and it's not fully that's Linux compatible, but we will keep improve this compatibility. Yeah. Let's give more information about the Quark containers architecture. The Quark container is running over the KVM. Yeah, and for the KVM, this is roughly KVM introduction. The KVM is in the KVM architecture. That's guest is running guest application is running inside a host user space, and in this KVM architecture, the host's application application will become the guest's physical memory, and host thread can be mapped to the guest virtual CPU, and we can switch between the guest and host through KVM. Let's go through KVM's KVM can provide some that's I/O control cores, and we can do the switch between them. And in the guest kernel, there will be just like a common OS. It provides page table process management, system call handling, etc. And VM and in the host space, there should be a VM virtual machine monitor. For the Linux VM, that is majority, that's the QMO. It simulates some block device and network device, etc. And for the Quark, it's different than the Linux VM. It's like the Linux virtual machine architecture, but there's some difference. Yeah, the right side is the Linux version architecture. It's running over the Linux kernel and have QMO, have Linux kernel and the Linux application. But for the Quark, it's also can run the Linux container application, but its VMM layer and the guest kernel layer is bundled together. That's Quark container. In the Quark container, it still split them as a QVisor is running in the guest in the host area, and the Q kernel running in the guest area. But they are developed together so that we can do some optimization to improve the performance. Yeah, and the Q kernel can only run over the QVisor, and the QVisor only support the Q kernel in this in the Quark. Yeah, in the Quark, we can do more optimization because Q kernel on the QVisor is bundled together. No. Actually, it's Quark is a kind of system call virtualization. It's unlike the normal Linux virtual machine environment. Actually, it is a kind of device virtualization. In the system, for the system call virtualization, we can do some optimization. For example, for the Linux virtual machine, the VMM, the switch between the VMM and the Linux kernel, it needs to go through the hypercore. The hypercore's cost is very high. When we do hypercore's work, is a switch between the guest space and the host space. Its overhead is high. It's because for the to switch from the guest to the host, it needs to save all the register, CPU register in the memory, and in the current advanced CPU, the CPU registers count is very much CPU registers. For example, the normal registers and also other things like the float point context, the cost to save them is high. But for the Quark, because the QVisor and the Q kernel are work together, so we can do some optimization. This one optimization that we can use a shared memory queue between the Q kernel and QVisor. So when the Q kernel need to send some call to the QVisor to run inside the host space. For example, run some host system call. It can they can queue the request to the shared memory queue instead of do the hypercall to do the switch, to do the context switch. There's a dedicated that's Q call, dedicated that's a thread in the QVisor. That's a Q call thread. It will get the request from the from the shared memory queue, so that it can so we can avoid the high cost that context switch. Actually, Quark do more optimization for this this request between the guest and the host. Another thing is we use IOU run. IOU run is a new IO infrastructure in the Linux. it is the most efficient way in the Linux kernel so far. The major concept of IOU run is that it will also set up a shared memory queue between the application layer and the kernel user space and the kernel space. So when user send a request to the send a system call to the kernel, it can include the request in the urun shared memory queue, and the Q kernel can get the request. A Linux kernel can get the request and process it. So we can save the context switch between the Linux user space and the kernel space. Similar thing, we can leverage this advantage in the Quark. Actually, Quark maps the IOU run shared memory queue to the Q kernel directly, so that when Q kernel need to run some system call in the Linux kernel, he can include the request to the IOU run shared memory queue directly, so that it can bypass the Q visor. So the communication between the Q kernel and the Linux kernel is through the IOU run queue. So it can make the performance can increase the performance. Yeah. Quark process is a normal Linux user space process. It's run inside a container runtime, Linux container. Normally, his performance should be less than the common Linux container. For example, run C. But in sometimes Quark performance can exceed run C. Because we are using guest, we can use a system call virtualization. Yeah.
Yulin, quick question. Yeah. If you can go back to the previous slide. So this is very interesting actually, because I was going to ask you that. I was looking at GitHub as well. This reminds me of, this is exactly what we were trying to do in the hardware enclave. When you do, the typically hardware enclave, SGX and all that, they don't allow you to do syscalls. So in order for you to do the syscalls, we had the similar kind of architecture. So the question I have is, so is this all asynchronous? So if I do from a user space application, I do a syscall. So I'm assuming you're going to trap it and then issue a function call. Is that function call synchronous or asynchronous? Because you mentioned the memory queue. I'm assuming it's async call, isn't it?
Oh, yeah, it's async one.
Okay. Yeah, go ahead.
Oh, but because the Q kernel also implement the kernel thread, so kernel thread, this Q kernel thread, kernel thread have the mapping, have the multiple to multiple mapping to the vCPU. So we can support this async call.
Okay,
got it. To the Linux container application, it is a synchronization call. Application just take a synchronization call, but in the Q kernel, it is async call.
Async call, okay. And then I'm assuming you have two different queues, or request queue and response queue, isn't it? Or is that one queue or there multiple two queues?
Oh, actually, that's a good question. A good question. Yes, actually, for the QLab, for the Q, that's QLab's shared memory queue. It is they have only one. That's submit queue.
Yeah.
Yeah. But for the return when they finish this Q call
response,
response one, because we have our own thread management, so the Q visor can just include the unblocked thread to the thread queue.
Oh, I see.
So it can process directly.
Okay. So and then the application waits up and everything, and you copy the buffers, from kernel space to user space and all that. So is that because this is exactly what we were doing in the hardware enclave thing as well.
Yeah. Actually, normally there should be two queue. One is a submit queue, another complete queue.
Response queue,
Yeah. The IO run take a similar thing, and for example, RDMA take a similar design. But just for the Q call, it's different because we own the thread scheduling, so we can do optimization. Yeah.
Okay. Are you doing any shielding? So when the response comes back from the kernel, what if the kernel is malicious? So if there's something wrong, as you, I'm assuming you're not doing that currently, but you should be able to do it though. You can have some kind of a shielding logic. If kernel gives you some kind of a bad pointer, and then you can detect that by using the shielding layer, and then you can reject that syscall response. And
oh yeah, yeah. Actually, kernel have full pager table just like Linux, and control all the memory used by the application. When application do some hack, for example, access kernels that's user kernel space, it can trap that.
Okay. Okay. So you have some kind of a shielding logic in there so that the kernel, when the response comes back from the kernel, from QVisor, so you can check if the pointers are not, malicious and all those kind of things. You can do all that.
Yes.
Yeah.
Your kernel have its own kernel pager table, and and kernel pager table and user pager table, and it is separate from the applications that's a Linux kernel pager table and the user pager table. It's a totally separate one.
No, but they're separate though. You still have to do copy though. So when the response comes back, when you do a buffer copy, what if the kernel gives you a bad pointer, malicious pointer, and then you can, it can destroy your application, for example. So
we will check that.
You check that. Okay. Good. Okay. Thanks. Thank you.
Thank you. Let's talk about the area we can do some better performance than the run C. One of the possibilities for the network. For example, we can use RDMA based container network. RDMA. I just gave a very high level introduction about RDMA. RDMA is a remote direct memory access, and for example, in the normal network, in the normal TCP network, that's protocol stack, application will send the request to the, when application want to send the data to the remote machine, it will send the request to the socket, and the socket will use the protocol stack, TCP protocol stack, send it to the NIC driver, and the NIC driver send it to the NIC, and NIC send it to the remote through the wire, and eventually go through the TCP/IP stack in the Linux kernel to the remote. But for the RDMA, the application can send the buffer to the NIC directly through the RDMA interface, and then RDMA that's RDMA ready NIC will send to the remote RDMA NIC, and then send to the remote applications that's user space buffer directly, so that they in the RDMA environment, it can the data transfer between the machines can bypass the Linux kernel and the Linux kernel protocol stack, so that its performance can increase dramatically. It both can increase the throughput and the latency, decrease the latency. But the RDMA is very good, and is maybe the most efficient that's network infrastructure in the cloud environment. But in the cloud environment, very like we didn't use that much, because the first one is that in the cloud environment, user use the RPC like the RDM, use RPC like the HTTP gRPC to do the communication. That's based on TCP/IP. But RDMA's syntax is different than the TCP/IP. That's the first one. And another one is more serious, is that in the cloud that's containerized environment, for example, the Kubernetes, they have container network. Container network is over the host network. It have another layer of virtualization. So virtualization and the network isolation. So it's hard to mapping the RDMA. The RDMA that's API to the container virtualization layer. Yeah. But for the Quark, we can leverage that. Yeah, we can use that TCP socket. We have implemented we have a design of TCP socket over RDMA. The major that's the major that's concept is that it's like this. For the client application, when they want to send some data to the server, and actually client application will have some send buffer. It will use a system call like the syssend to the kernel. That's syssend is send data through the system calls, that's socket interface. And the syssend will when the Quark to process the syssend, it will copy the application send buffer data to the kernel send buffer. And normally, Quark can use the host's kernel's that's the TCP stack to send to the remote. But for the RDMA syntax, RDMA's context, the Quark can use the RDMA write to write to the remote buffer of remote's Quark's kernel receive buffer, and then copy it to the application receive buffer. Go through this way, we can see the Quark can bypass the host TCP/IP stack and also the guest TCP stack, so it can improve the performance. Yeah, this is a major concept. Actually, here because we have less time, so I didn't go through the virtualization that's design. But we have tested this concept and get a very good performance. Yeah, let me give you. Yeah.
Hey, Yulin, a question for you. So I recently saw somebody told me that the gRPC. So if I'm using gRPC, and you mentioned that gRPC uses TCP underneath it, but gRPC, they've added RDMA as a protocol as well, though now. So you can run gRPC over RDMA. So would that have any implications on your design or what you're doing?
Yes, gRPC actually is over the TCP. TCP still use this socket layer. It uses maybe syswrite something. Yeah, but it's still over the TCP. So because the Quark just use RDMA to implement.
No. What I said was gRPC. They've added RDMA protocol, so you can. So the application developer can still do RPC calls.
Oh, I see. I see.
Yeah.
Yeah, but that's I heard that. But there's another challenge. Just like I mentioned, there are two challenges to use RDMA in the cloud environment. The first one is to just gRPC over RDMA. Another one is virtualization. You know that container have container network, and container network have virtualization layer. If you use RDMA directly over RDMA, if we want to use that in the container environment, we still need to solve the container network virtualization.
No, I see. Yeah.
So, but for the Quark TCP socket over RDMA, we solve both of them. So both.
Okay.
Yeah. We can see the performance. So far, we haven't finished all the implementation, but we have already finished a test, a POC test. We can actually in the POC test we test the TCP over RDMA for the radius that's with radius benchmark. We can say that's for the radius environment with one thread, that's Quark performance throughput, that's Quark over run C. For the one thread, that's Quark's throughput is 2.4 times of run C's throughput. And this OPI and PB is two benchmark in the radius benchmark. Here we can see they have more than 2 times of performance improvement. Another is the latency. That's P1, P99, and average, etc. And RDMA have maybe this is a 1/4 latency. and 1/5 latency, 1/3 latency over RON-C's implementation. But in our POC, we find that if there's multiple multiple TCP connection, that's multiple thread, our performance will not so good. Will still be better than RON-C, but not so good. But we still do the improvement in our production implementation. We may release this implementation in a few months, in 1 or 2 months. We can release our first production release for this TCP or RDMA. Yeah. In our POC, we found that in our POC, our TCP connection and the RDMA connection, RDMA have a connection named Q pair. They are 1-to-1 mapping, but in our production implementation, we found that in our POC, we found that if there are more TCP connection, this 1-to-1 mapping will decrease the performance. So in our production environment, implementation, we will use multiple TCP connection over single or a few that's RDMA connection, so that we can improve performance, and it can finish in a few months. Yeah. Yeah, this is TCP or RDMA, and yeah. Another thing is we already test the Quark performance and compare with Kata and the T-Visor. We can find that its performance is better than them. For example, this is start time. That's comparison. In this comparison, we can say that's RON-C. If run a simple application, its start time is about 600 millisecond, and Quark is a little over the RON-C. T-Visor is over 700 millisecond, but Kata is much higher. Your Kata will start the full Linux kernel. Yeah. Another is the memory overhead. All this comparison is based on the RON-C. For the Quark, it will spend maybe 12 megabytes more memory than the RON-C. T-Visor need to spend 28 megabytes, and Kata need to spend about 200, almost 200. Yeah. And another thing is for etcd benchmark test. Normally, that's Quark is better than the T-Visor and the Kata. Yeah. This is throughput. We can say Quark is actually so far. This is the old test result, but in the new test result, Quark is sometimes is better than the RON-C, and much better than the T-Visor and the Kata. Still, for the radius is a similar thing. That Quark is much better than the T-Visor and the Kata. Here, this NGX actually still the old that's the test. In the new test, Quark is a little smaller. That's the problem is a little less than the RON-C, but much better than T-Visor and Kata. In the latest test, Quark's performance is 3 times of T-Visor, and maybe 4 times or 5 times of Kata's throughput for the NGX. Yeah, we also test some other tests for the MariaDB, MySQL, and yeah, in majority the environment that's Quark is better than the. Yeah, that's all. Any question?
Thanks for the presentation. One question, just kind of to wrap my head around it. What are the similarities between the G visor and Q visor, apart from the name? Are they related? Like, is it did you guys fork it from G visor, or how do they relate with each other?
Oh, actually, actually, Quark and T-Visor share same kind of how to say it, same kind of concept. We all use QEM as to do isolation and have our own, that's our own how to say it, different our own, that's kernel table, just like only that's change automate the version of Linux kernel. We implement that, but T-Visor implement that with Go language, and Rust implement Quark implements Rust language, and we share different architecture.
Okay, so it's a completely different implementation.
Yeah.
That's what you're saying. Okay.
Completely different.
Okay,
Yeah.
okay, I understand. Okay, thanks.
But the concept is the same. G-Visor guys are very different than Kata and all those guys, because they have this user land. They do everything at the user land level. And that's exactly what Quark does that as well. But yeah, the concept higher level is the same. But as the Quark is much more, performant, and you can see that the RDMA and everything.
Yeah. For example, T-Visor use Go languages, that's GC. So, but Quark have our own, that's memory management, the heap management, and for scheduling, T-Visor use Go languages, thread scheduling, but we implement by ourselves, and we also have our Q core, hypercore, and the IOU run and the RDMA. But T-Visor just use a common, that's a hypercore. Yeah.
Interesting slide. Do you maybe have this similar comparison with the Firecracker? Because I guess the concepts are not so similar there.
Firecracker is much different. Firecracker actually just use a full Linux kernel. The difference is it just optimize the QMO, but they still use the Linux kernel. So maybe Kata and the Firecracker is a similar.
Yeah, they're both virtual machines.
Yeah.
Well, yeah, the Firecracker can run as part of the Kata framework, basically.
Yeah.
Okay, thank you.
Thank you.
Good, thanks. Anybody else? Any questions? We can't really do voting for this because we don't have a quorum. So I only see 3 out of 7 TSC members on the call. So we can maybe do voting via email. But if anybody has any questions, otherwise we can move on with the next agenda item. Thanks, Yolin. I appreciate it. This is really looks very good. Thank you. Anybody else has any questions before we move on? The next agenda item is the work our Click to Cloud team did for the Edge Cloud as part of our Edge Cloud, the Centaurus Edge Cloud thing. So who wants to, how much time would you take? Because we have only like 20 minutes left. Would that be good enough? Or should we punt it to next TSC call? What do you guess?
I think that's enough for us, Deepak.
Okay.
So from our side,
Go ahead. You guys take over then.
Yeah, sure. Thanks. So from our side, Roshan and team is there. So hey, hi Ashwin, are you there? Ashwin and Dashera, are you there?
Hi.
Yeah.
Yes.
So guys, please share your screen and showcase whatever we have done for next. Okay. Till now the progress with Deepak and the team. Okay, please go ahead.
Pang is not there actually, so he's not there on the call. That's another one. Oh shoot. If that's something, you know what? I think that's not good because Pang is the one you work very closely with.
Yes, definitely.
So I'm wondering, he's not there. I think we missed. I don't think he has this call on his calendar. We forgot to invite him. I would recommend actually. Yeah, go ahead.
Sorry to interrupt. We have invited him in last week meeting, so he asked us to show the live demo in this meeting, but unfortunately he didn't join this meeting.
Oh no, because I bet you the reason he didn't join because this meeting is not on his calendar. So I sent you guys a calendar, to everybody, but I forgot to include Pang in this call. So would you guys, I think in order for this meeting to be productive, what if we just move this to next meeting, next month's meeting?
Yeah, that's also fine for us.
Because
like,
I'll get more people from my Edge Cloud team, actually.
Yeah, that will be great.
Yeah,
like
because-
there will be more people and we'll get
Yeah,
more
yeah,
clarity
yeah.
on that part.
Yeah, because I don't see anybody from our team. I know the Professor Sharam and Stefan, they have a pretty good, the Edge background. They've done very expensive work. But in our team, I want our team to be there as well. Especially the Edge Cloud, Pang, and a bunch of other guys. So I don't see them, and it's my fault actually. I should have invited them. And plus the fact that we may not have enough time to go over this. But I'm pretty sure you're gonna take at least half an hour though, isn't it? This thing. In any case, I would recommend we push this to next meeting. Is that okay?
Yeah, that's okay. That's okay, Deepak.
And
No
we'll make sure Mangani and I will make sure that our team, our Edge guys are on the call as well.
Yeah, sure, definitely, Deepak.
Okay, great. Thank you. I appreciate it. Sorry about that. I know I know I invited a bunch of people and I forgot to invite Pang, even though he was aware of it, because if the meeting is not on your calendar, you don't really know. So you might have forgotten. So. Okay, I think, yeah, thanks. I appreciate that. And then we will move this to the next this agenda item to next month. And in the meanwhile, the Quark container work. So if you guys, so now we have some time. If you you have any question about Quark, feel free we can chat more if you want. Otherwise, we can wrap this up, this meeting. Anybody? No?
I think no from our side. Yeah.
Okay, thank you everybody for joining. So we'll send out, I'll send out an email voting for this Quark container to be in. The intent is we would like to, I mean, if the TSC committee approves it, we would like the Quark container as a runtime, as a workload to be part of, just like Docker container, to be part of Centaurus project. So I will send out, well, I think that before we do that, I know a couple of members, TSC members are already there. What's your perspective on that, Professor Dustar and Stefan, on the Quark container?
I think it seems like a nice technology. It seems similar to gvisor, basically on the concepts, etc. But the implementation seems to be much better. The question, if we can, I would need to look a little bit more into the performance side of things. So potentially to explore if it would make sense maybe to bring this to the edge as well. That would be a, one interesting possibility. Yes. If that's possible, obviously, but for those things that the resource constraints, etc., are important. But yeah, definitely, I think we should allocate some time to explore this further together.
But one thing I do want to let you know, I think Yulin can talk more. That's what our intent is as well. Yeah.
It makes sense. Yeah, I noticed that you guys are kind of trying to optimize the whole thing and to kind of make it faster and smaller. So, and this is actually also something that we've been working on some years ago. But I think the technology is now much more ripe, so to say, to actually do this and to do this in a really kind of production ready way. Obviously, what another important thing is how does this fit with the general ecosystem? So how much of the tooling can we reuse for those things? For example, for provisioning, for deployment, etc. Or do we have to also, or should we?
Actually, Yulin, you may want to talk about, because it's a seamless experience. Yulin, why don't you go ahead? Yeah.
Oh, yeah. Actually, now we want to make the Quark runtime just like the Kata and the gvisor. And for the tooling part, for the container level like debug in future, it will be same as a kata and the T-visor. There's be no much difference. Yeah.
Same image, same Docker image will work. Everything will work the same.
Yes, exactly. Yeah.
Yeah, I think these things are very important, obviously.
Yeah, you have to be backward compatible, otherwise, yeah.
Yes, and you want to fit in also with the entire ecosystem, basically.
Current tooling and all that, yes.
Exactly.
So that's very important, very important.
Yeah, definitely. I mean, I shared this already internally as we were speaking, as Jungmin was speaking with the team, and it sounds really interesting. And I think we'll have a look at this a little bit more, and then maybe we can also have, let's say an offline session where we do a little bit deeper technical dive, because
Sure.
I think there are some interesting questions which I still would like to have clarified, in particular, with the whole architecture and then the individual parts, how they're implemented and how they work. I think that.
But at the high level, though, you think it's a good. I know the GitHub has a lot of information, but I think maybe we can expand more. Yulin, actually, the picture you have, maybe we can expand, because that optimization piece is very important. Actually, that's the key of all that. So if we can maybe explore that more in the documentation to kind of, I think that would be really just one comment from my side.
Okay.
Yeah. Because that's the most important thing, the whole IO optimization and how this whole flow works, the thread, you have 1-to-M, you mentioned 1-to-M thread and all of these things. And, then the request queue, response queue, and the reason you didn't have a response queue because we control everything. So we should really document, because that's the very core of all that, actually. See, I think we should document that much better.
Yeah, I will do that.
Yeah. Okay, and but other than that, you a high level from a voting perspective. I mean, let me send out an email so you guys can respond to it.
Yeah, no, definitely this should be a part of the project for sure.
I think so. Other than that, we're done. Thank you very much. Thanks everybody for joining the meeting. So we'll meet up next month.
Thank you very much, Deepak, everybody.
Thank you.
Bye-bye.
Bye-bye.
Thank you, Deepak. Bye-bye.
Bye-bye.
Thank you.
Thank you, everyone.
Bye-bye.